Welcome to the History Maps podcast. Today we are doing a deep dive into the source material covering Inca technology. And our specific mission here is to deconstruct how an empire stretching entirely across the Andes managed to engineer solutions to some of the most complex geographical challenges on Earth.
Right, and they did all of this without the tools we typically assume are strictly necessary for large-scale imperial infrastructure.
Yeah, exactly. I mean, when you look at the historical record of modern empires, you look for iron forging, you look for the wheel, you expect to find heavy draft animals and a written alphabet.
Right.
And if a society lacks those tools, the standard assumption is usually that they just can't engineer on a massive scale. But the Inca built mathematically complex and seismically secure infrastructure out of raw earth, grass, and woven hair.
It is a totally different engineering paradigm.
Mm.
And the sources we are looking at today provide a very multidisciplinary breakdown of how they pulled it off.
Yeah, we're going to look at everything from the seismic rigid body dynamics of their stone walls to optical fire starting devices.
And we'll also break down the topological data encoding they used, to run an entire empire without ink or paper.
Let's start from the ground up, literally. The foundation of this empire sits on a highly active tectonic zone.
Yeah, it's a landscape that is constantly trying to shake itself apart.
Right, so you are standing on a steep Andean ridge. An earthquake hits. If you are in a structure built of modern, rigid steel or poured concrete, you just have to hope those materials don't reach their breaking point.
Because if they do, they fail catastrophically.
But the Inca took a different approach with their masonry, right? I keep thinking about the sheer weight of these stones. Wouldn't a rigid stone wall just tear itself apart during a major tremor?
Well, that is the exact problem they solved. And to understand it, we really have to look at their high-status stone masonry. The sources distinguish between two main types.
Okay, what are they?
First, you have coursed ashlar masonry. That is where rectangular stones are laid in flat, horizontal rows, sort of like a standard brick wall.
Right, pretty common.
But the technique that requires really intense analytical focus is their polygonal masonry. These blocks have irregular geometric shapes. They're meticulously fitted together like a massive three-dimensional jigsaw puzzle.
And the sources refer to the exterior faces as pillow-faced, right? Because they bulge outward slightly.
Yeah, exactly.
But how are they extracting and shaping these massive irregular blocks? Because, I mean, you can't carve a precise jigsaw piece out of granite without hardened iron chisels.
Right. They relied entirely on the physics of percussion and expansive force. So instead of iron, the masons used hammerstones.
Just harder rocks.
Yeah, exceptionally hard, dense rocks, usually quartzite or chert.
Right.
And by striking the bedrock repeatedly with angled blows, they flaked away the softer stone to dress the surfaces.
Okay, but what about actually extracting a 200-ton block from the quarry?
For that, they would chisel a line of small, deep holes right into the rock face.
And then they just hammer wedges into those holes to split it.
They did use wedges, yeah, but it wasn't purely brute force. They often used wooden wedges, driving them tightly into the holes, and then they would soak that wood with water.
Oh, because the wood expands when it gets wet.
Precisely. The natural cellular structure of the wood absorbs the water and expands. So you get this slow, massive hydrostatic force that cleanly splits the rock slab right along the fault line.
That is, I mean, it makes sense. And then they just pry it out.
Yeah, using heavy bronze pry bars to lever it away from the bedrock.
Okay, so they've extracted it. But the logistics of moving these things, some of these blocks weigh up to 200 tons, and they don't have wheeled carts and no oxen.
Right. No draft animals heavy enough for that.
So how are they moving a 200-ton stone?
They used earthen ramps and just vast amounts of human labor. They pulled the stones using incredibly thick ropes made of braided ichu grass.
Grass ropes pulling 200 tons.
Yes. And if you look closely at the physical evidence left on the stones themselves, you can see how they did it. A lot of these blocks still have protruding nubs near the base.
The sources called them lifting bosses, right?
Exactly. These nubs provided a secure anchor point. Workers would tie their grass slings around these bosses, drag the stones up the ramps, and lever them into their final positions.
And they just leave the nubs there.
In many cases, once the stone was perfectly seated, the masons would chisel the nubs off for a smooth finish. But they left enough behind for us to understand the method.
I am still stuck on the idea of them perfectly seating an irregular stone. I mean, we are talking about dry stone construction here.
Right. Mortarless.
There is no mortar on the exterior to fill the gaps. The faces meet so tightly you can't slide a knife blade in there. So how do you get a 200-ton geometric block to sit flush on the irregular block material.
The sources highlight a specific scribing technique. First, the bottom of the top stone is carved with a concave bedding joint, so it cups the slightly rounded top of the stone beneath it.
Okay.
But to get that perfect fit without lifting a 200-ton stone up and down repeatedly just to check the seam, they likely suspended the new stone slightly above its destination.
And then traced it.
Yeah. They would use a plumb bob or a scribing tool to trace the exact contours of the lower stone directly onto the upper one.
So the outside is a perfect, mortarless puzzle.
Yes. But the sources also point out a hidden structural detail. Deep inside the core of the walls, where the irregular shapes didn't meet perfectly, they packed the empty spaces with a sticky red clay called lonca.
Oh, okay. So it's dry fitted on the outside, but clay packed on the inside. Let's go back to the earthquake scenario, though. Why doesn't this massive mortarless wall just shatter?
Modern engineers have run finite element analysis on these structures. They model the Inca wall as a multi-rigid body system.
What does that mean in practice?
It means that because the stones are so precisely carved, there's a very high uniform coefficient of friction across all those contacting surfaces. So during a minor tremor, that friction holds everything together. The wall acts as a single solid mass.
But minor tremors aren't the real issue in the Andes. What happens when a magnitude 6.0 earthquake hits?
That is when the physics completely change. The analysis shows that when a seismic event reaches a peak ground acceleration greater than 0.2 g.
Which is severe enough that a person can barely stand up, right?
Right. At that level of force, the uniform friction is overcome. A rigid wall of steel or concrete starts to fracture because the stress has nowhere to go.
Right.
But the polygonal masonry blocks actually separate slightly. They lose contact with each other for a fraction of a second. They essentially shift and dance in place.
And that movement desiccates the kinetic energy of the earthquake.
Exactly. It absorbs the shock.
I mean, we rely so heavily on unyielding materials in modern construction, but the analogy that comes to mind is comparing this to a solid pane of glass in a window frame.
Okay, also.
Well, if the frame shakes violently, the glass can't bend, so it just shatters. But the Inca wall is more like a precisely packed box of irregular geometric wooden blocks. If you shake the blocks rattle and shift to absorb the energy.
That is a very accurate way to visualize it.
Right. But when the shaking stops, why don't they just stay a jumbled mess?
Because of two specific design choices. First, those concave bedding joints act like self-centering mechanisms.
They guide the stones back down.
Yes. And second, the walls were built with an inward batter. That means they slope slightly inward toward the top. So gravity pulls the shifting blocks down and inward, forcing them to lock right back into their original jigsaw configuration.
You can really see this at the fortress of Sacsayhuaman above Cusco. They have those massive cyclopean stones forming zigzag defensive walls.
Right, or the 12-angled stone in Cusco itself. It's a single block with 12 distinct corners fitted perfectly into the surrounding stones.
And that extreme irregularity eliminates straight fault lines, right? So you don't get stress concentration points that would tear the wall apart.
Precisely. They engineered a way to survive the movement of the earth itself.
But that introduces a secondary problem. If your whole structural philosophy relies on stones shifting without mortar, what happens when it rains?
Water management.
Yeah, water has to be meticulously redirected. Because if it just washes the soil out from under the stones, the walls will collapse, earthquakes or not.
And water management was an existential requirement for them. Just look at the environmental data for Machu Picchu. It was built around 1450 on a really steep mountain ridge at about 2,430 meters elevation.
And the sources say that specific ridge receives nearly 2,000 millimeters of heavy rainfall annually.
Exactly. 2,000 millimeters of rain on a steep ridge with mortarless stone walls.
The threat of landslides must have been constant. A single bad storm season could have just washed the whole city off the mountain.
It was the primary threat. So to prevent it, Inca engineers integrated fluid mechanics directly into their urban planning. If you walk through Machu Picchu today, there are 129 formal surface drainage outlets built right into the retaining walls.
129. But those are just the surface drains. The most vital engineering is actually underground.
Yes, the subsurface drainage. Before they even built the visible structures, they excavated deep into the ridge. They laid down this incredibly thick layer of rock chips, gravel, and waste stone from the quarries.
So it acts as an infiltration reservoir?
Exactly. When the torrential rains hit, the surface water percolates down through the topsoil really quickly and hits that highly permeable subterranean layer.
And that stops the water table from rising and saturating the soil above it.
Right. It acts like a sponge. It temporarily stores the massive influx of rainwater and then slowly and safely drains it away from the structural foundations.
Because without that crushed rock layer, the hydrostatic pressure behind the walls would just blow them out.
Complete structural failure, yes.
So they drained the destructive rainwater away, but they also had to bring clean drinking water in. The sources detail this primary canal cut directly into the mountain to feed Machu Picchu.
The main canal is 749 meters long. It taps into a natural spring higher up the mountain, and the engineering precision here is really in the slope.
It was built with a steady 3% grade along its entire length, wasn't it?
Yes, and that specific incline wasn't random. It was calculated to deliver roughly 300 liters of water per minute. That provided a steady flow into a sequence of 16 publicly accessible fountains.
And there's a really interesting social hierarchy built into those fountains. The very first one in the sequence, the one getting the purest water right from the spring, was reserved for the emperor.
And the sources note that his bathing room had a completely isolated drainage system. That way, the bath water wouldn't re-enter the public supply.
Which shows a really clear understanding of urban sanitation. But to see their absolute mastery of fluid dynamics, we have to look at the Taipan Royal Compound near Cusco.
Taipan is where the sources suggest their engineering actually anticipated modern fluid mechanics.
Yeah, I want to spend some time on this because it's fascinating.
Well, at Taipan, the agricultural terraces and water channels are built on very steep mountainous terrain. And when water flows down a steep incline, it naturally accelerates. If it moved too fast, it reaches highly erosive velocities. It would just scour out the unlined dirt canals downstream and destroy the agricultural fields.
So to stop that, they manipulated a specific fluid dynamics metric. Modern engineers call it the Froude number.
Yes.
And just for you listening, the Froude number is a dimensionless metric in modern physics. It basically determines the behavior of a fluid in a channel by comparing its inertia to the force of gravity.
Right. So when a channel has a Froude number less than 1, the flow is considered subcritical. It's deep, it's tranquil, and it's slow-moving.
But when it's greater than 1, the flow becomes supercritical.
Exactly. Supercritical water is shallow, extremely fast, and highly destructive. The Inca engineers designed the principal channels at Taipan to maintain a Froude number right between 0.8 and 1.2.
That is such a narrow margin, they kept the water flowing in a stable, near-critical state.
Balancing speed and safety, yeah.
But how do you achieve that level of mathematical precision just using carved stone channels?
By manipulating the cross-sectional geometry of the channel itself. At the principal fountain in Taipan, the main channel width is 0.9 meters.
All right.
But right before the water drops to the next level, the stone channel abruptly narrows to 0.4 meters.
So it's less than half the width.
Yes. This physical contraction forces the fast-moving supercritical water to bottleneck. The kinetic energy crashes into itself, causing the water to abruptly slow down and increase in depth.
And in modern hydraulics, that's called a controlled hydraulic jump.
Exactly. The jump dissipates the water's destructive kinetic energy right there in the stone basin. So the water flowing out the other side is slow and safe for the earthen canals.
This brings up a major question for me. We are sitting here talking about Froude numbers and supercritical flow. Did the Inca have, a formal mathematical theory for calculating fluid dynamics on a chalkboard? Or was this purely empirical trial and error?
There is no evidence they used Western algebraic formulas to calculate flow rates.
Because controlling a hydraulic jump with carved stone sounds incredibly complex. But if you think about it in tactile terms, it's really just like holding a flowing garden hose.
Oh, that's a good way to look at it.
Right. If you put your thumb over the end of the hose, you restrict the exit, you change the water's velocity and pressure, you can create a gentle fan of water that doesn't disturb the soil, or you take your thumb off and a hard stream digs a hole in the dirt. It feels like an intuitive physical understanding of how shape dictates flow.
The physical model analogy is exactly how they approached it. They relied on rigorous empirical observation, physical modeling, and generation after generation of refinement. They understood deeply that the physical geometry of the channel dictates the energy of the water.
So they were probably tracking flow rates during different seasons and adjusting the stones based on that data.
It was an empirical, tactile science. But the results perfectly align with modern hydraulic engineering principles.
Okay, so we've established how they survived earthquakes and tamed destructive water. That flows right into the next hurdle, the soil itself.
Geotechnical engineering.
Right. You've controlled the water, but how do you use these steep Andean slopes to grow crops without losing all your topsoil to erosion?
We have to look at the Andes, the massive agricultural terraces that define the landscape there. The goal was to create flat, arable land in an environment that naturally offers none, while preventing heavy rains from washing that new land down the mountain.
The physical construction of these terraces is far more complex than just building a wall and dumping some dirt behind it. It's a highly specific layered system.
The stratigraphy of an Inca terrace is really a masterwork. The process started with the stone retaining wall, which was built with that same inward batter we discussed for stability.
Right, sloping inwards.
But behind that stone face, they didn't just pour in topsoil. The first layer at the very bottom was composed of large, rough rocks.
Okay.
Above that, they laid a stratum of smaller rocks and gravel. On top of the gravel went a layer of sandy material. And only at the very top did they place the nutrient-rich agricultural topsoil, which they often hauled up from the valley floors.
So I'm picturing a massive, multi-layered filtration cake built directly into the side of a mountain, layer by precise layer.
That filtration cake is exactly how it operated. They built drainage outlets directly into the stone retaining walls, positioned at the level of those large base rocks.
So when the torrential rains fall, the water doesn't pool on the surface and wash the topsoil over the edge?
Exactly. It percolates straight down. The topsoil holds the moisture the plants need, but the excess water quickly filters through the sand, then the gravel, and finally hits the large base rocks.
And then it just flows horizontally through the gaps and exits safely through the drains in the wall?
This system completely eliminated surface soil erosion. The topsoil remained perfectly intact and leveled, decade after decade.
The retaining walls are fascinating too because they serve a dual purpose. They hold back the soil and house the drainage, but there's also a critical thermal property at work.
Right. The stone retaining walls act as massive thermal batteries. During the day, the high-altitude Andean sun is very intense, and the large stones absorb a tremendous amount of solar radiation.
And then, as the sun sets and the temperature on the mountain plummets toward freezing,
Those stones begin to slowly radiate the stored heat back out into the air immediately surrounding the terrace.
so this thermal mass effectively creates artificial frost-resistant microclimates right on freezing mountain slopes.
The ambient temperature just above the soil on the terrace stays several degrees warmer than the surrounding air.
Which means they could cultivate crops at elevations where the natural climate would have instantly killed them. The sources briefly mention the Three Sisters planting method used in these microclimates.
Yes, growing corn, beans, and squash together in the same soil.
It demonstrates deep botanical science working in tandem with the geotechnical engineering, because by planting those three crops together, they created a symbiotic ecosystem.
The beans extract nitrogen from the air and fix it into the soil, fertilizing the corn.
And the corn stalks provide a natural trellis for the beans to climb.
Meanwhile, the large leaves of the squash plant spread out across the ground, acting as a living mulch that shades the topsoil, retains moisture, and suppresses weeds.
They maximize the nutrient yield of the soil within these highly controlled microclimates. So the engineers have tamed the earth, the water, and the soil. They are producing massive amounts of food. This transitions us to a critical logistics problem.
Because growing a surplus on a mountain is useless if it rots before you can transport it.
Exactly. The logistics of feeding an empire spanning thousands of miles required a massive leap in food preservation.
And the Inca achieved this by utilizing the natural extremes of their macroclimate to create tuño, which is a freeze-dried potato.
We usually think of freeze-drying as a highly modern process, vacuum chambers and industrial machinery. But the Inca managed it using only the weather.
The environmental requirements are highly specific, though. You need an elevation above 3,800 meters, and you need the winter nights to drop to a specific temperature range between -1.4 and -5.0 degrees Celsius.
The process itself is a brilliant exploitation of those diurnal temperature shifts. After the harvest, the villagers would just spread the potatoes out on the ground, exposing them to the freezing air overnight.
As the temperature drops below freezing, the water inside the potato cellular structure freezes and expands. And this physical expansion ruptures the cell walls of the potato.
So the freezing actually does the mechanical work of breaking the potato down internally.
Yes. And then the next morning, as the intense high-altitude sun rises, the ice inside the ruptured cells melts.
And this is where the human labor comes in.
Right. At this point, the villagers walk over the potatoes, systematically trampling them with their bare feet, Because the cell walls are broken, the trampling acts like squeezing a sponge. It forces the liquid water out of the tuber while discarding the tough skins.
And they don't just do this once, they repeat this freeze-thaw-trample cycle for several consecutive days. The sources also mention a washing phase, which dictates the final product.
If they want to produce white chuño, known as maraya, they soak the trampled potatoes in cold, running river water for several weeks.
To wash away the bitter glycocolloids, right?
Exactly, before leaving them to dry. If they skip the washing phase, they produce a darker, more bitter variant called black chuño.
And the final step is just sun-drying.
They leave the processed tubers exposed to the parched alpine wind and the harsh sun for anywhere from 12 to 37 days, until absolutely all the moisture is drawn out. They also applied a very similar freeze-thaw dehydration technique to camelid meat, like llama and alpaca.
Right, creating a preserved meat called charqui, which is actually the linguistic root of the modern English word jerky.
It is.
And by removing 90% of the moisture from a potato, the logistical impact on the empire is staggering. They essentially created a feather-light, highly durable military ration.
A porter or a llama caravan can carry vastly more calories if they aren't carrying the water weight of the food.
Right, but the durability is the true technological triumph here. A properly prepared batch of chuño has a shelf life of up to 10 years without any refrigeration.
To illustrate how effective this is, the sources cite an archaeological excavation at Tambo Viejo. This is an ancient Inca settlement located in the arid coastal desert of southern Peru, far from the freezing highlands.
And what did they find?
Archaeologists unearthed an intact ceramic vessel hidden beneath the floor, and inside it they found dehydrated potatoes that were 500 years old.
500 years.
The food remained perfectly preserved for half a millennium. It proves it could be transported from the freezing mountains down to the hot, dry coast without spoiling.
But storing food that lasts 10 years requires vast infrastructure. The empire built storehouses specifically for this purpose called cuelcas.
The cuelcas were massive logistical hubs. They were usually circular or rectangular stone structures built high on the hillsides above the settlements.
To exploit the cool, constant, dry mountain breezes, right?
Yes, and they were engineered with underground ventilation ducts and small slits in the walls to ensure a continuous flow of air around the stored food. That completely eliminated the stagnant moisture that causes mold.
The scale of this storage network is hard to even comprehend. The state built thousands of these cuelcas. Some administrative centers had hundreds of them clustered together in long rows.
They stored thousands of tons of chuño, charqui, and maize. This massive decentralized surplus mitigated the risk of localized famine and allowed the empire to project power by feeding armies on long campaigns.
Okay, so we have thousands of tons of featherlight, freeze-dried food safely stored in ventilated silos. But moving that food across the empire brings us to the next massive engineering challenge.
The geography.
Right. The Andes are scarred by incredibly deep gorges and rushing rivers. How do you march a fully loaded llama caravan across a canyon when you don't use the arch or wheeled carts?
The solution was the suspension bridge. The Inca road system relied on a vast network of rope bridges constructed from organic fibers, primarily ichu grass and cabuya fiber.
And these were not small footbridges. They were heavily engineered structures capable of spanning up to 50 meters across deep canyons.
To contextualize that, a 50-meter clear span bridge made entirely of grass outperformed the heavy masonry bridges being built in Europe during the exact same historical era.
The tensile strength they achieved with grass is remarkable, but the construction of these bridges relied heavily on a highly organized, state-mandated division of labor.
The process began with the women of the local communities. They were responsible for harvesting massive quantities of the tough highland ichu grass.
And they would pound the grass with stones to make it pliable.
Right, and then braid it into thousands of meters of thin, strong cordage. The scale of the materials required is immense. Once the women produced the base cordage, the men took over the heavy assembly.
The men would take those thin braided cords and twist them tightly together to form much thicker ropes, right?
And then they braided those thick ropes into massive main cables. These main support cables could be up to 30 centimeters thick.
30 centimeters thick.
And a single section could weigh over 200 pounds.
That is a massive cylinder of tension fiber. The physical rigging of those cables across a 50-meter gorge over a raging river must have been incredibly dangerous work.
The on-site rigging was definitely the most perilous phase. They would use a very thin, lightweight line thrown or carried across the gorge to slowly pull the heavier cables over the expanse.
The engineering brilliance lies in how they anchored these massive loads, though. On both sides of the canyon, they carved deep abutments into the solid bedrock.
They would wrap the heavy main cables around massive stone beams seated in these abutments. Teams of men would then haul on the cables, tightening them inch by inch, leveraging the stone beams to remove the slack.
And create the massive tension required to support the weight of the bridge deck, which was also woven from branches and grass.
Exactly.
I want to focus on the tension aspect. You mentioned earlier that these cables could support the weight of 100 people, or a fully loaded caravan of llamas. But because the entire structure is made of organic grass, it is constantly degrading.
Right. The wind, the rain, and the sun rot the fibers.
So the material life cycle of ichu grass meant that the bridges were temporary structures. For safety, the imperial administration required every major bridge to be completely dismantled and rebuilt every single year.
But this constant cycle of destruction and reconstruction is precisely how the engineering knowledge was maintained and transmitted. We can see this in practice today at the Kiswachaka Bridge, which spans the Apurimac River.
They still rebuild it.
Every June, 4 local Quechua communities gather to cut down the rotting bridge from the previous year. Over 3 days, using the exact same division of labor and weaving techniques of their ancestors, they braid new cables and weave a completely new bridge.
They are transmitting a 500-year-old engineering schematic through physical practice.
Yes.
The physical, tactile nature of this engineering is what fascinates me. The sources mention a project where students at the Massachusetts Institute of Technology attempted to build a 60-foot replica of one of these grass bridges.
And they struggled.
Right. It really highlights the difference between theoretical and tactile engineering. You can understand the math of tension and load-bearing vectors on a chalkboard, but understanding how a 30-centimeter bundle of braided grass behaves under massive tension.
How it stretches?
Yeah.
How it grips the stone abutment?
Yeah, how it responds to the wind. That kind of engineering cannot be learned in a classroom. It can only be learned by physically manipulating the fibers.
The physical properties of the material dictate the engineering approach.
Yeah.
You have to feel the tension to understand the bridge.
And that concept of manipulating fibers brings us directly to the data infrastructure of the empire.
Which is completely unique.
Yeah, if you have an empire that stretches for thousands of miles, moving thousands of tons of chunyo across hundreds of grass bridges, you need an administrative database to track the labor, the taxes, and the inventory.
And the Inca managed all of this data without ever inventing a written script. They used physical threads to bridge informational gaps.
We need to talk about the quipu.
The quipu, sometimes spelled quipu, was their complex data recording device.
Oh.
Physically, a quipu consists of a primary horizontal cord from which hang numerous pendant strings.
Right.
A small local quipu might only have a dozen strings, but massive imperial administrative quipus could have hundreds or even thousands of pendant strings cascading from the main cord.
And the data was encoded and read by highly trained specialists known as quipu kamayaks. Let's break down the mathematical logic of the quipu, because it's not just random knots.
Not at all.
It operates on a base 10 positional system, which is conceptually identical to our modern decimal system.
The position of the knot on the pendant string dictated its decimal value. The knots clustered near the top, closest to the main cord, represented the highest values, so the 10,000s or the thousands.
And as you move down the string,
The positions represented hundreds, then tens, and finally, the knots at the very bottom represented single units.
and the type of knot tied in each position communicated the specific digit.
Exactly. To represent the number 1 in the unit's position, they tied a figure-8 knot. For the integers 2 through 9 in the unit's position, they use a long knot, looping the string around itself the corresponding number of times.
So 4 loops for a 4, 7 loops for a 7.
Right. But for the higher decimal positions, the tens, hundreds, and thousands, they used simple overhand knots. If they needed to record the number 300, they would tie 3 simple overhand knots in the hundreds position on the string.
But the most mathematically sophisticated part of this system is how they represented nothing. Crucially, the absence of a knot in a specific decimal position equals 0.
Which is a huge mathematical leap.
Yeah, so a string with 3 overhand knots at the top, a blank space in the middle, and a figure-8 knot at the bottom represents the number 301. Using empty space to represent 0 is a highly advanced concept.
But the database was not limited to numerical knots. It was a multi-dimensional storage system. The physical knots were just one axis of the data matrix.
They also utilized color to encode qualitative information, right?
A quipu could feature up to 24 distinct standardized colors. They derived these brilliant dyes from natural sources. They utilized crushed cochineal insects to produce a vibrant red, or the indigo plant to produce a deep blue.
So the data had color coding built into its physical structure. A red string might tally military figures or casualties, while a yellow string could represent the state's inventory of gold or maize.
Furthermore, the actual direction that the thread was spun and plied, whether twisted to the left or to the right, could encode binary information.
Like indicating whether a tax was owed or had already been paid.
Yes. It is important to note, though, that the quipu itself was a storage device, not a calculator. Before Quipucamayoc tied the final knots, they would perform the mathematical calculations using a separate device called a upana.
And the upana was a grid carved into stone or wood, right?
Yes, with distinct compartments. It functioned much like an abacus. The administrator would move physical tokens like seeds or small pebbles between the compartments to calculate the census data or the labor quotas.
And once the calculation was verified on the upana, the final figures were permanently recorded by tying the corresponding knots onto the quipu. I always wonder about the security of this data.
How so?
Well, if a runner drops a quipu on the road and a commoner picks it up, can they read the empire's tax records? The format feels inherently encrypted. Comparing it to modern data systems, the quipu is much closer to a three-dimensional binary code than it is to a written document on a piece of paper.
The comparison to encrypted code is highly accurate. An ordinary farmer might understand a very simple string with a few basic knots used to count his personal herd of llamas.
But the imperial records.
The massive, complex imperial quipus were completely illegible to anyone without specialized training. The specific combination of color, knot position, thread spin, and hierarchical cord attachments meant that the quipu was an exclusive administrative language,
It was a secure database woven entirely into physical form.
readable only by the Quipucamayocs.
And the precision required to twist, dye, and knot those fibers for data encoding blends seamlessly into the technology that the Inca prized above all else, their textiles.
We often view textiles purely as clothing or art, but for the Inca, the loom was their most sophisticated technology. In their value system, fine textiles were far more precious than gold or silver.
The mechanics of their weaving relied on the backstrap loom. This is a highly portable, elegant device where one end of the loom is tied to a tree or a post and the other end is strapped around the weaver's lower back.
The weavers uses their own body weight to perfectly control the tension of the warp threads.
And using that body tension loom, the weavers achieved a thread density that rivals modern industrial machinery. They utilized extremely fine wool sheared from vicuñas and alpacas.
The sources note that in the highest quality garments, they achieved thread densities of up to 600 wefts per inch.
That's incredible. And the socioeconomic function of this cloth, particularly the highest grade known as kumbi, was central to the functioning of the state.
Kumbi was not produced casually. It was manufactured in massive state-sponsored workshops. The labor was highly organized, performed by the Aklala, the chosen women of the empire, alongside male weaving specialists known as Quipucamayocs.
This fine cloth functioned essentially as the imperial currency. It was used to pay tax obligations, it was given to the military as compensation, and it was the primary diplomatic gift used by the emperor to secure alliances with newly conquered territories.
But the technology extends beyond the sheer density of the thread. There is structural data embedded directly into the patterns of the fabric. The designs woven into the kumbi were highly codified.
Right, the elite garments featured complex checkerboard patterns known as tkapu.
These geometric squares conveyed specific information about the wearer's social rank, their ethnic lineage, and the universal order of the empire.
Furthermore, the very structure of weaving, the constant rhythmic crossing of the warp and weft threads, created a pervasive over and under motif that the Inca used to represent the deep interconnectedness and reciprocity of Andean society.
The cultural dominance of this textile technology was so absolute that it heavily influenced their other engineering disciplines, even their stonework. We see that clearly when looking at the earlier Tiwanaku culture, which heavily influenced Inca aesthetics.
Yeah, if you examine the massive Tiwanaku stone sculptures, notice that the monuments are carved with flattened, highly blocky surfaces.
The sculptors were not attempting to depict realistic human anatomy or musculature. Instead, the stone is shaped specifically to act as a flat canvas to display the intricate geometric patterns of the textiles the figure is wearing.
The fabric itself was the most important message being conveyed, even when working in solid stone. We've covered so much ground here. We've explored how they engineered stone to survive the moving earth, how they manipulated fluid dynamics,
How they layered soil to build microclimates.
how they used thermodynamics to freeze dry food, how they tensioned grass to bridge canyons, and how they encoded data into woven hair. But to close out the body of this discussion, the sources describe a highly specialized technological outlier that feels completely unexpected.
It involves their understanding of optics.
Yeah.
The sources contain a fascinating historical account from the chronicler Inca Garcilaso de la Vega detailing the Inti Raymi Sun Festival. During this critical religious ceremony, the high priest of the sun would wear a large, highly specialized bracelet on his left wrist, known as a chapana.
And this chapana was not just a piece of decorative jewelry. Attached to this bracelet was a highly polished concave vessel.
It was functionally a parabolic mirror. The chronicler describes it as being shaped like a half-orange, highly polished to a mirror finish. During the climax of the ceremony, the high priest would raise his wrist and angle this concave reflective surface directly toward the sun.
Because of the parabolic geometry of the vessel, it captured the incoming solar radiation and focused all of those scattered rays into a single, intense point of light in the center.
Precisely. They would take highly combustible material, specifically finely unraveled, highly dry cotton, and place it exactly at that focal point.
And in a very short space of time, the concentrated solar energy gathered by the parabolic mirror would cause the cotton to spontaneously combust.
Allowing the priest to start the sacred fire using only the power of the sun.
This specific detail highlights a profound contradiction that I think redefines everything we have discussed. We are repeatedly told that the Inca were a society that lacked the technology of the wheel.
Right.
Yet, they possessed the sophisticated understanding of metallurgy to forge a reflective vessel, the understanding of optics to capture light, and the understanding of advanced geometry to shape that vessel into a perfect parabola in order to focus solar energy into combustion.
It forces us to heavily scrutinize the metrics by which we measure technological advancement.
It leaves you with a very profound concept to mull over. The Western definition of what constitutes advanced technology is incredibly narrow. We have heavily biased our historical grading system toward the forging of iron, the rolling of wheeled carts, and the scratching of ink onto paper.
But the Inca Empire built a sustainable, mathematically complex, and seismically secure civilization entirely out of the raw earth, the grass beneath their feet, and the woven hair of their animals.
Their data, their logistics, and their infrastructure were literally woven into the physical world around them. It makes you deeply consider what a modern, highly digitized society, a society that relies so heavily on rigid, unyielding panes of glass and invisible digital clouds that we cannot touch, might lose when the power grid finally goes out, compared to a civilization that understood exactly how to rebuild its most vital bridges by hand from the grass up every single year. Thank you for listening. History Maps. Learn history visually.